In this video, I'm covering a simple example from the text that illustrates this idea of trained least squares linear equalization. So the way he sets up this problem is interesting. He comes up with an output equation for the received symbol sequences, all right, received symbol values, and it turns out they're a function of the previous symbol multiplied by a plus the value of the signal at k minus 1. So the optimal case would be we only have signal values, right? We're only receiving signal values, not some corrupted version of the signal values. All right, I say signal, I mean symbol values. All right, so in this particular example, he's looking at binary symbols. So the two symbols are -1 and 1. All right, and so what we have here is a sequence of 5 symbols that are being received, and he's going to apply this channel distortion and then see if we can come up with a matrix formulation that undoes the distortion from the channel. All right, it's an interesting example because if you've taken DSP, you would have known that this is an IIR filter. Okay, so it has an infinite impulse response, so it's not constrained to a certain time interval. And yet here we have an equalizer that is a finite order, a finite impulse response equalizer, and it'll still be able to do the job. All right, so if you haven't had DSP, don't worry about that comment. All right, so the first thing I want to do is show you how the channel is applied to give you distorted signal values. All right, so we start with some initial condition. All right, so he's going to start with 0.8, and that's just a number pulled from the air. All right, it could have been anything. Of course, the value that you start with affects everything else moving forward. So it's not like you pull it out of the air and then nothing happens. You pull this 0.8 out of the air and it determines what happens for the rest of the received signal sequence. Okay, so it was given in the problem statement that this coefficient A is equal to 0.6 and B is equal to 1. Okay, and so what I wanted to do is trace your way through this output equation. All right, so with this output equation, we know that we take this 0.8 that shows up here and we move it as r of k minus 1 to get r of 2. So r of 1 shows up here, okay, and then we do the calculation where the symbol values we start plugging in, so I've color coded these, so this 1 moves to here and we get this output 1.48. All right, then that output 1.48 is plugged into the next difference. All right, so when we get R3, it's 0.6 times the old value. All right, so plus the new symbol value, and the symbol value is shown in red. Okay, so that gives us an output value. And so once again, you take that output value and you plug it in. You take the next symbol value, you plug it in, and you get the next output value of the channel. And you just keep going. This goes to here. And we get the final output value of the channel, which I neglected to write down, but turns out to be 0.3597. Okay, so I didn't have enough terms here. All right, so at this point we have the received signal value, and you notice these don't look like symbols, right? They're pretty far off from what we know to be the symbols. All right, so next we want to apply a linear equalizer. So the linear equalizer is just these coefficients. In this case, we only need 2, f0 and f1, And so we take f0, we multiply by r of k, we take f1, we multiply by r of k minus 1 to get the yk symbol. All right, so we've talked about this before. These symbol coefficients add up to k. So 0 plus k is k, 1 plus k minus 1 is k. All right, so that's one way of thinking of how that filter applies. Okay, then the point that the author is trying to make is, oh, look at, if you make f0 equal to this, 1 over b, and if you make f1 equal to minus a over b, and you plug that back in, plug these specific values back in, and use this symbol sequence, all right, into this equation, you will get back the symbols, all right? So remember, the symbols were binary values in this case. And so you will get back the symbols. All the other distortion would have been removed. Okay, so that's the point of this example. And what I'm going to do next is I'm going to pick it up in MATLAB so that we don't have to look at all the tedious calculations. But you'll see how to set that up in MATLAB. And we'll go through this and do a calculation. Okay, so picking this example back up in MATLAB. All right, in the example, he's defined the channel. So we've already talked about that. We defined the channel here. And he says, oh, here's the answer. If we had this as the answer, you plug r of k back in like he's doing here and here, and you back substitute, then the answer turns out to be s of k minus 1, which is the symbol values, which is, you know, exactly what you wanting the equalizer to produce, the symbol values before the channel distorted those. Okay? All right, so what I want you to take a look at is how you form these matrices. All right, so down this column, you have s of 3 through s. Well, I'm supposed to go down a column, but it won't let me select that in Acrobat. But you look at this column-wise, we're forming these columns, S3 through 5. I'm going to stop doing that because it doesn't work. Okay. And then we start S2, S3, S4, and then finally S1, S2, S3. So you form these columns, and you do the same thing with the R values, and the way he's getting that is from the definitions that he set up before. All right, remember, we're trying to accommodate any given delay delta. Delta is the delay, and alpha effectively shows the range of the delay. All right, so we know somewhere between 0 and alpha is the true parameter delta. All right, so we set up this S vector by starting at alpha plus 1, all right, and you go up to P, all right, and you just keep going like this until you form this pattern. So I've coded that in MATLAB, all right. Same thing for R, you encode this pattern that you see in MATLAB, all right. From there, you get this potential array of equalizers, all right? And which equalizer you choose depends on which gives you the lowest mean squared error, okay? So you calculate the mean squared error for each optimal equalizer, choose the best one, that's your answer. Okay, so over here in MATLAB, I have this programmed, all right? So remember the things we did. I showed you how to do this hand calculation where you put in this difference equation, all right? So if you'll recall, we talked about this right at the beginning of the course, that the A vector gives you the feedback terms on a IIR equation. So A equal 1 goes in front of R of k, and then the next coefficient, if you move the R of k to the other side, it shows up as a minus 0.6, so that goes here. And then the only thing on the input side of the equation is S of k minus 1. So there's
0 s of k plus 1 times s of k minus 1. So that's the b vector. All right, so plug into this filter BAS, and then this particular example starts with an initial condition that's non-zero. Okay, that's a little bit unusual. I understand why you put it there, but we have to have some initial condition. If you started from 0, it would take too long to get up to steady state, so he gives it a little nudge of a head start. So, all right. So the point is, when I do this filter command, these numbers should look familiar to you because we've already calculated those by hand. All right, so it's implementing this channel distortion that we've modeled by this filter. All right, so in MATLAB, we program the S matrix and the R matrix, and we do this by starting at k equals 0 to alpha to get the S values. So I'm essentially programming each column of S and forming new columns. All right, so when I get done with that, I get this array that shows up in the book right in here. Okay. All right. Similarly, for the R column, we go from 0 to n. All right, so we need as many R's as there are the filter order. All right, so that's how many columns we have. All right, and so we form each column at a time, and you look at that definition in the book. Here's the definition of the R matrix. We've programmed that in MATLAB. So I included this because you may need to do that whenever you're actually implementing a matrix form of an equalizer. Okay, so the next thing in the book that he talks about is simulating not only the effect of channel, but also the effect of some noise. All right, and so when you do this R matrix, you get exact values for R, and if you round those off, all right, and assume those are the received values, then they're different, right? You know, instead of 0.112, we get, minus 0.112, we get minus 0.1. So in a way, you can consider that as a noisy version of the R matrix. Okay, you could do this without noise, but you know he throws some noise in there as well. All right, so the next thing we do is we program this phi matrix. Okay, because the phi matrix is what's used to determine where the minimum of the cost function occurs. All right, so remember, the cost function is written as a phi matrix plus some other stuff, and the other stuff doesn't depend on f, and we only care about the effect of f. So if we minimize phi, we are minimizing j. All right, so we don't keep track of the total mean squared error, we just look at phi. Okay, so I do that, and I look across the diagonal, and what shows up in the diagonal is actually the value that we're trying to minimize. All right, and so we see here on the second row and column, all right, we get the minimum of phi. All right, so that tells us we need to take the second row, the second column, to get the optimal coefficients for the linear equalizer. Okay, so I set that up in MATLAB to actually pull off those minimums. The minimum occurs here. That's column number 2. I pull that out, and I get the exact values that show up in your text. Okay, and so he makes the point in here that if you look at this value, it's pretty close to what he said the optimal would be. He said, you know, the first coefficient should be 1 over b, which is 1. All right, 0.9548, reasonably close to 1. And the second one should be minus a over b, which turns out to be minus 0.6. And this is reasonably close to minus 0.6. Right, so if you filter that, now you get things that look closer to the symbol values, and you could plot the soft decision diagram, but it's so sparse, it's hard to make much sense out of it. All right, like there's the original. Okay, yeah. Here is the answer after you do equalization. Okay, so what I wanted to do at this point is to generalize this example a little further. What if we took a lot more signal values, all right, and performed this equalization step on this whole range of trained sequence values or symbol values? Okay, so that's what I did here, and in fact, I wanted to show you you don't have to rely on the fact that this is a binary set of symbols. All right, so I'm going to comment that out. This is my RANPAM, so I know that's producing symbol values like we've seen for our 4PAM project. Okay, so I run that. And I get this symbol sequence, 500 symbols, lots of symbols here. All right, I still have a received vector. The values are different because the symbols are different, right? Instead of binary, it's now 4 symbols. But you get the point. You have this received vector, right? I had the same formulation for generating the S matrix. It's just bigger now because I have a lot more symbols. Same thing happens with the R matrix. It's bigger because I have a lot more symbols. I'm still simulating the noise. That's not super relevant to this example, but it's an added bonus, I guess you'd say. All right, and now I look through here and I calculate this phi matrix, all right, and it's still minimized at the second diagonal element. Okay, and so I pull off this as the optimal coefficients, and it's interesting because I have a lot more data. I get a lot closer to the true optimal values. All right, it's not exactly right because I've added a little bit of noise in there, but it's only off here in the tens of thousands digit. Okay, so I get these optimal filter coefficients, and when I apply this filter to the received output of the channel, I can now do an eye diagram that shows the soft decisions. So the soft decisions before I ran it through the equalizer, that doesn't look like distinct symbols, right? We know there should be 4 distinct symbols. The channel has distorted this quite a bit. You can't pull out the unique symbols, right? But after I do the filtering, it definitely lines things up and I get this eye diagram that looks normal to me, right? Normal in the sense that it's clearly producing output symbols like I expected. Okay, so to quickly summarize, we went through this example. It's a small example where we used a little IIR filter to simulate the effect of a channel. All right, we put all the data into the right matrix format, implemented the solution completely in MATLAB, and then we were able to show a soft decision diagram that looks like it's working and it's opening up the eye for communication through this distorted channel. Okay, so take a look at that. I urge you to kind of play around this, handwrite out these matrices so you can understand exactly how things are being put together. And then, again, it's like this, optimizing this quadratic where we find the filter according to the matrix calculation. All right, so hopefully you'll find that helpful for trained least squares equalization.